Okay. Okay. Yeah.
Right, good afternoon, everyone. I'm trying to control the noise. Otherwise, if your mic continues making noise, I'll take you to the waiting room. I normally want to take charge of my class. So if you cannot take the responsibility of your microphone, I'll move you out of this class and put you in the waiting room. Make sure that you monitor the activities of your microphone. Okay. I welcome you all to our first online lesson in computer studies. And today, I would want to introduce the topic on the logic gates. And I hope you pay attention because towards the end of this lesson, there is an assignment that I'm going to give you, and its due date will be tomorrow at 18 hours. Failure to it, you shall see me during SBA results. Okay, let me just try to get my pencil. Okay. So we are looking at the logic gates. And when we talk of logic gates, we are talking about a system that uses the numbers which are zeros and ones, and the logic gates are the building blocks of any electronic components, like the motherboard of the computer, the motherboard of your remote control at home, and anything that is electronic in nature is made of what we are calling the logic gates. And by definition, logic gates are the building blocks of computers. So it means the entire circuit of computer is made of the logic gates. And you'll be able to understand these logic gates as we go into the details. When you say logic gates, just know that they are the basic building blocks of a computer system. So there are various types of logic gates that we are going to look at. We'll look at first the NOT gate, the AND gate, we'll go to the OR gate, and we are going to end with we'll end with a NOR gate. We'll also look at the Nanji Gate. This one mostly is outside the scope of your syllabus, but we don't know how far the ECZ have changed the curriculum. So not today, but soon we'll later look on at the XOR gate. And our first target is the NOT gate. A NOT gate or any other gates, they've got what we call the truth table. And this truth table gives results based on the logic gate you are using. The result for the AND gate are different from the results of the NOT gate. They're also different from the result of the OR gate. So the truth table is able to show you the name of the logic gate we are using at that instance. So Building a truth table is not a job. You have to pay attention to details of what we are going to discuss. Otherwise, you won't be able to finish your logic gates. And the first gate, like Gary mentioned, it's a NOT gate, which is also known as the inverter. A NOT gate sometimes is not known as the inverter. And its job is simply to invert. If the input is 1, the output is going to be 0. A 1 in the computer studies, like we discussed on the binary numbers, is got, we call it a high. And then a 0, we call it a low. So what happens in a NOT gate? If the input is low, the output is always going to be high. And if the input is high, the output is always going to be low. And the physical symbol of a NOT gate is given by this symbol. This is the symbol. Equally, the Chinese uses this other symbol. It has got that O in front there, and this is what inverts the input. If you enter a 1, when it comes here, it will be converted to a 0. Equally there, if you enter a 1, if it passes through that O, it will bring out a 0. So that is a NOT gate. It's an inverter. And a NOT gate, when a 0 is entered, the output is a 1. When a 1 is entered, the output is a 0. So when you look at a truth table, this is the truth table right here. And it shows that when the input you enter in the circuit is a low or a 0, the output is always going to be a high or a 1. And when the input is a 1, the output is going to be a low. What you need to understand by now is that the symbol for a logic gate, which is a NOT gate, is given by this symbol. And in the exam paper, they don't indicate that this is a NOT gate. By its look, you're supposed to know it that this is a NOT gate or it's not a NOT gate. So that is the first gate. The second gate we are going to look at, it's the AND gate. The AND gate, mathematically, it's given by A times B. A times B is equal to X. So when you say AND gate, it has got a mathematical symbol, which is A. If it's 1 times 1 is equal to 1, like that. That is the mathematical symbol. It goes with the multiplication symbol. When you're talking of the AND gate, you're talking about multiplication. That is the first thing. Then the symbol is different from the NOT gate. Like we saw, the NOT gate is something like this. That shows that this one inverts when it's 1, it gives a 0. When it's 0, it gives a 1. But the AND gate, when you're using the AND gate, by definition, it produces a high only when all the inputs are high. That's the definition of the AND gate. Looking at the truth table, only when both of the inputs are high, then it will give you a high. Anything less than this, it's going to be a low there, and a low there. Only when all the inputs are high, when it's a 1, it will give you a 1. So what we do with these inputs, first let's look at this symbol for the AND gate. Like this symbol, AND gate, it has got 2 inputs. And remember that they are given by that mathematical symbol there. A times B is equal to X. X is the output. Just as you can see from this truth table, A, they said it's 1, another A, it's 1. Then the output is going to be 1 when both of the inputs are 1. If one of the input is 1, the other one is 0, the output is always going to be 0. Then, how do you come up? How do you draw, a truth table? If they say, they can give you this gate here, and then they say, draw the truth table for this gate. So to understand that, like you were saying, the Nandi Gate, the line here is straight. Then we've got possibly, according to our question, we've got two inputs. So if they ask you to draw the truth table for this one, you're supposed to first look at the number of inputs. And when you're coming up with the variables of input, what you're going to do is you're going to say n to the, 2 to the power n is equal to x. X is the output. Then 2 to the power n. N are the number of inputs given. Like in this situation, we've got two inputs, A and B. So you'd say 2 to the power 2 is equal to 4. This is the first stage you must deduce before drawing a truth table. And the truth table can carry a minimum of 8 marks. So you're supposed always to remember that given a logic gate, I'll use this formula. All types of logic gates, you're going to use this formula, 2 to the power n is equal to x. Then that n is the number of inputs you are going to be given. If they gave you that the number of inputs, they are 3, then the possible output is going to be, variable inputs is going to be 8. So looking at this scenario that we were looking at in this situation, we have two inputs. So if we have two inputs, we are going to use 2 to the power n to give us the number of inputs that are going to be, we are going to use in a truth table. So if we find that there are two types of input, we are going to have what we call a 4 variables. So what is the meaning of this? This is what I'm trying now to explain to you on the board here. We've got two inputs. We've got A and we've got B. These two are inputs. But for us to find X there, how are we going to draw the variable of inputs? We're going to use 2 to the power n is equal to x. And there are two types of inputs from our PowerPoint presentation. So we would say 2 to the power 2, and the result is 4, which means before the input before the output there. That's why you start counting. You will start with the zeros until they are 4. You start with the 0, 1, 0, 1, until they are 4. 1, 2, 3, 4. That is the meaning of this formula. Always next to the output, the variable which is there, you follow this syntax. You start with 0, 1, 0, 1. Then the next one here, the next one there, you say 0, 0, 1, 1. To remind you of the binary thing that we used to do in class, when we were drawing a benchmark for converting binary numbers, we were starting with 1, then 2, 4, 8. I think you recall this benchmark I drew for you in class. So the first one there, it's saying that in this region will be having 1, 0, 1, 1, just like that. So it says 0, 1, 0, 1. Then when we move to the next, which is here now, it is the second one, which is 2. So it's going to have 2 zeros, 2 1s, 2 zeros, 2 1s, just like that. If there was another variable there, which could have been C, then we go to the fourth one, which means you're going to have 4 zeros, 4 1s, just like that. And these numbers 1, 2, 3, 4, they are coming from 2 to the power n is equal to 4, where n is the number of inputs you are given. So This is where what we are able to see from our PowerPoint presentation here came from. There is 0, 1, 0, 1. When we go to the next input there, we've got 0, 0, then 1, 1. Okay, so if you were drawing the truth table for this type of a gate, which is the AND gate, it was going to be like this. In the exam room, they will just possibly give you a logic gate like this. Draw the truth table for this logic gate. The first thing you're going to identify is what is this gate? And obviously, this gate, the symbol shows that it is the symbol of an AND gate. What do you know about an AND gate? That's when you come to the output there, that it only gives out a high or a 1 if both of the inputs are 1. This is very critical because in coming up with these values, if you make a mistake, you forget this principle here. And then you forget that it's 0, 1, 0, 1. Then the two numbers are going to coincide where they're not supposed to coincide. And you end up getting the wrong output there. So be careful on that one. Moving forward, we look at the OR gate. Just like the AND gate was giving us multiplication in between there, the OR gate gives us addition. When you're dealing with OR gate, it means you are adding. And unless in the AND gate, where this line was straight here, in the OR gate, it's a little bit curved there. And that is the difference between what you saw in this symbol for the AND gate. There it is straight. But in this gate, there it is a little bit curved. Then when it is like this, you even know that this is the OR gate. So there we've got the AND gate, and here we've got what we call the OR gate. And it's when drawing the truth table, it's the same principle. You're supposed to use that formula to come up with the number of variables you're going to have as the input, where 2 to the power n and n is equal to the number of inputs. Since in this example, we've got 2 inputs, there is only A and B to produce the output. So we are going to have 4 variables. If you have 4 variables, then you start with the one that is closer to the output. You say 0, 1, 0, 1. They are 1, 2, 3, 4 because of this principle there. Then from there, you jump to the next one. You know that in the binary benchmark, we said start with 1, then you go to 2, then you go to 4. So the first one there, we are getting 1, 0, which means the next one, we're going to have 2 zeros. The next one, we're going to have 4 zeros there. And that is why there is 0, 1, 0, 1. In the next one, when we jump, we're going to have 2 zeros, 0, 0, 1, 1. Why are we ending at this level? We have been restricted by this formula that the variable output, they're only going to be 4. Because 2 to the power 2 is equal to 4. That n stands for the number of inputs. Next, there is what we call the Nanji Gate. So the most serious and important gates that you fully need to remember is the NOT gate, the AND gate, and the OR gate. If you understand these 3, you are not going to have any problem with the rest of the gates. So please understand the OR gate, the AND gate, the NOT gate. These 3 are very important, because if you understand this, then the rest of the gates, like the Nandi Gate and the NOT gate, they are not going to be a problem because they are built using these 3. And as we move to the Nandi Gate, we are going to build a Nandi Gate using these 3 gates. And you'll see how we are going to achieve that feat. So, looking at the Nandi Gate, my system is freezing. Okay, there. So, the symbol for the Nandi Gate, there is what we call the Nandi Gate, first of all. Then the N stands for the Naughty Gate. So this gate has more than one gate in it. In short, it is a circuit. A circuit is any gate which has more than one logic gate. So we've got N for Naughty Gate, then we've got the AND gate. And if these two are combined, we are going to get the Nandi Gate. And the symbol for the Nandi Gate, first you draw the AND gate. Then by the end there, you put the symbol for a Naughty Gate. They are combined together. This is the official symbol. Although in some books they print something like this, but the official one is this. And that is what we call the Nanji Gate. So mathematically, the AND gate is A times B. AND gate is A dot B, or AB, which is A times B is equal to X. For the Nanji Gate, the only difference is that it also follows the mathematical formula of the AND gate, but you're supposed to put the bar at the top there. When there is a bar there, then you know that this is not the AND gate, it is a Nanji Gate. Then graphically, we are going to see that it's going to have that not symbol there. So, which simply means this is the Nanji Gate. And when drawing this symbol, it has a principle to draw it. And this is the principle. A Nanji Gate produces a low output only when all the inputs are high. If all the inputs are high, there is one there and there is one there, it will give you a 0. That is the principle of a Nanji Gate, nothing more. Anything less than that, it's going to be high. If the lows are the same, if these are the same, they are both zeros, then you're going to have a high. If one of them is high, then you're going to have a high. Just like that, you get a high. It will only give you a low when both of the inputs are low. Remember, in the OR gate, it gives you a high only if there is a high in the input. Whether there is 0, as long as there is high, there is a 1, it gives you a high. And the OR gate can only produce the low when both of the inputs are low. So systematically, starting from the NOT gate, it gives you a high when the input is 0. It's an inverter. It converts from the input, what is there, to the opposite of what is supposed to be the output. If it is 0, the output is going to be 1. That is NOT gate. Then the AND gate, it produces a high only when both of the inputs are high. Then when we come to the OR gate, it produces a high as long as in the input there is a high. So there can be only one there, the other one is 0, it will give you a high. Both of them can be 1s, it will give you a high. But as long as both of them are 0s, it will give you a 0. So this OR gate, when we look at the Nanji gate, that's where there is going to be a 1. A Nanji gate is only going to give you a 0 when both of the inputs are 1. So you can compare this OR gate, it gives you a 0 when both of the inputs are 0s. Then that one will give you a 0 when both of the inputs are high. So there is a direct conflict between these two, the OR gate and the Nanji gate. The OR gate has only 1 0. That is when both of the inputs are 0. The Nanji gate has only 1 0. That is when both of the inputs are high. And obviously, that's the logic circuit of the Nanji gate. The last one we are looking at today is what we call a NOR gate. So there is the OR gate, and there is what we call a NOT gate. They are combined. Just like the OR gate, its mathematical symbol is A plus B. If you are drawing a NOR gate, you just put a bar at the top. Then you know that this is no longer a OR gate, it's a NOR gate. And the graphical symbol is similar to that one of the OR gate. On that, there is that NOT symbol at the end there. Then you will know that this is not a OR gate or an OR gate, this is a NOR gate. And by its definition, in a NOR gate, a high output is produced only when all the inputs are low. So look at this. When both of the inputs, they are low, they are all zeros, it will give you a 1. And if you've got a very bad memory, you mess up these things in the exam room and you end up failing. So this calls for consistency and a coordinated effort for you to understand them. You will fully understand this when we look at the first example on how these questions are prepared. So remember, a NOR gate will give you a high when both of the inputs are low. So taking you back a little bit, this one, the OR gate, it will give you a high as long as there is a high in the input. There can be 1 and 0, 1 and 1, but as long as there is a 1, it will give you a high. Anything less than this scenario, it will give you a 0. If we go to the next one, which is the Nanji gate, this one, they are saying that when both of the inputs are high, it will give you a 0. And it quarrels with the AND gate, because the AND gate, when both of the inputs are 1, it gives you a 1. The Nanji gate, when both of the inputs are high, it gives you a 0. And that's what we are getting at the Nanji gate. Look at the OR gate. At the OR gate, when both of the inputs are 0, it will give you a 0. Now look at the NOR gate. When both of the inputs are 0, it will give you a 1. Let us fully understand this using this example. So the first thing that we have, they are saying that draw a truth table. You pay attention to this, otherwise you fail the assignment. Draw the truth table of the following circuit diagram. So before you started drawing, the first thing, look at the input. How many inputs are there? 1, 2, 3. Then we even know that 2 to the power n is going to be our x. And in this scenario, it is 2 to the power 3, because we've got 3 inputs. Then the variable outputs, they are going to be 8. That should click first. We've got A, B, C as input. So you even know that in our truth table, we are going to have 80 variables as the input. That is the first thing you're supposed to understand. So before we go into the details of this, let's put this one together on the board. Okay. So we've got 3 inputs. And now we're going to do it. We're going to say 2 to the power 3 is equal to 8. Then we've got the input 3. There is A, there is B, and there is C. These are the 3 inputs. We are drawing the truth table. Then the output there is X. I mean, there can be any number as output or later. But for me, I normally use X. So when you start now drawing, putting in the variables there, we know that they're supposed to be 8. And then the first one is 0, 1, 0, 1. They are 4. We need to do it again, 0, 1, 0, 1, like that. Now they are 8. 1, 2, 3, 4, 5, 6, 7, 8. The next one, this is where we get a 2. We are going to have 0, 0, 1, 1, 0, 0, 1, 1. Then the third one, like from the benchmark for in binary, it's 1, 2, 4, 8. We are at 4. So then we're going to have 1, 2, 3, 4 zeros. Then we are going to have 4 ones. This is the first thing that you are going to do. Before I can continue, if there is a question, you can raise up your hand. Anyone with a question? You can see everyone is okay. Let me just, Madaliso, are we clear?
Yes, sir.
Okay. There is a question from Lumba, Tierra, and okay. Let me start with Lumba. Yes, Lumba, any question? Oh, sorry, you're on mute. Any question, Lumba? Yes, Tierra.
So when solving, you have to put the truth tables also.
The truth table is a must, Tierra. It's a must. When solving, you start with a truth table. And this is what I'm starting with. Okay?
Okay.
Okay, yes, Costa.
I didn't hear what you said when you started writing on the board, sir.
Okay, what I've drawn there, you didn't get what I was saying?
Yes.
All right, okay. I'll repeat that. Yes, Lumba.
How did you get to when you're handling the B column?
The second column. All right. Okay. Okay. So, boys and girls, what we are looking at here is this question here. Okay. This is a serious example we are looking at. They are telling us that can you draw the truth table of the following circuit diagram? That's the question. So before you started drawing this circuit, the truth table, you first count the number of inputs. After counting the number of inputs, then you convert how many outputs are we going to expect by using this formula 2 to the power n. And n is the number of inputs, and the inputs, they are 3. So you're going to have 2 to the power 3. And the result, obviously, as a mathematician, you know that it is 8. I hope that is clear before I proceed. So from there, this is where I was saying that before we can answer this, we can look at this and that one. We first need to draw the truth table. And the truth table is exactly that, the one I'm trying to put up on the board. So it's going to be like this. 2 to the power 3 is equal to 8. So we know that our variables, they are going to be 8 inputs. So now, from this question, as you can see, there are 3 inputs, A, B, and C. So since there are A, B, and C, these are the ones I'm trying to put there. You can put them in any order. It's A, B, and C. And I can say A, B, and C. Doesn't matter as long as you follow the protocol. Then these 3 inputs are supposed to produce the output, which I'm calling the X. So what I was trying to explain that if you remember on the binary benchmark I gave you in class, we were starting with 1, then 2. These numbers were building up by multiplying it with a 2. So there is 1 times 2, 2 times 2, 4 times 2, 8 times 2. I think you remember this. And Lumba, we interacted about this thing on social media, I think WhatsApp some time back. So the first one here is this one, which is saying that here it's going to have 1, 0. So throughout, you're going to have 1, 0. But the total number of values there are going to be 8 because of the 2 to the power n is equal to 8, where n was equal to 3. So what we are going to say, we'll start with 0, but because we had the first one, 1, 0. Then 0, 1, 0, 1. So 1, 2, 3, 4. They're supposed to be 8. We continue. 0, 1, 0, 1. Like that. Then the next column there, we are at 2. There will be 2 zeros. So there is 0, 0. Then 2 ones, 1, 1. Again, 2 zeros. Then 2 ones. Then when we come to the third one there, we are jumping now to 4 zeros, 4 ones. And we're going to say 0, 0, 0, 0. Then 1, 1, 1, 1, in that fashion. So you start with the number of 0 as indicated in that benchmark. So this is the first thing you are supposed to do before you can even go further in answering the question that we have been posed with. Just trying to make sure that everything is in order there. So there is 0, 1, 1. Okay. So there. So far, what we have tackled on is that we have drawn the truth table without finding the outputs. Now, the next thing, very important thing, is understanding this logic gate. And from what we are looking at, let's look at what we've looked at. We looked at the NOR gate. And they are telling us that this is a NOR gate. And in a NOR gate, we said that it produces a high when both of the inputs are zeros. If the inputs are zeros, it will produce a 1. Then the rest of the things, it's zeros. So when you look now at our problem here, they are saying that this is a NOR gate. And we know the principle that it's going to produce a 1 when both of the inputs are low, because it's a NOR gate, as referred to the NOR gate there. It's producing a high when both of the inputs are zeros. So since we remember this, what we are going to do now is we look back at A and B because this NOR gate has the input A and B. That's what we're going to start with. And it's a NOR gate. So let's look at the board now. Okay. It has A and B, and it's a NOR gate. And we know that it produces a high when both of the inputs are low. So the problem that we are going to have there is that if you critically look at this, look, what we are getting here is not the X, because the output we are going to get here is going to be the input for the next gate. The output also we are going to get there is going to be the input of the next gate. This is the reason why we need to use common sense, that the value we are going to get here is also going to be the input for the next stage. So that is the reason why here I had put a P, there I had put a Q. but you want to be told to do that. I just use the common sense. So the output I'll be getting here is going to be P, and the output I'll be getting here is going to be Q. So to solve this question properly, I'll do it like this. I'm going to include P there. I'll include P, and I'll include Q out of the understanding of the question. Not that you'll be told to do this. You look at the question. If there are more outputs being expected, then you do the needful, like what I've just done there. And then the questions are saying that we are looking at A and B, which is a NOR gate. So a NOR gate is going to produce a P. So we just look at A and B as in this question. Please don't get lost. As in this question, we are looking at A and B. They are the ones going into the NOR gate there. So what we are going to do now is this. A and B, we know that here A is 0 and there A is 0. And we've discovered that when both of the inputs are zeros in a NOR gate, it produces what we call a 1, according to this scenario. Okay, according to freezing. Okay, according to this, as long as it's NOR gate, it gives you a 1 when both of the inputs are zeros. So that's what we have here. A and B are going into the NOR gate, and we are going to do exactly that. So they're going to a NOR gate, A and B. When A is 0 and B is 0, it gives us a 1. When A is 0, B is 0, it gives you a 1. A is 0, there is a 1, then it will give you a 0. Because this scenario can only give you a 1 when both of the inputs are zeros. So there are both of these two are zeros, both of the inputs, means it gives us a 1 at P. We are solving at P according to the question. So if we solve at P, now we go to Q. If we find the Q, that's when we can get to X. So look at Q now. Q is there. At the input, we've got B is coming all the way to Nandi Gate, and C is coming all the way to Nandi Gate. And we discussed that the Nandi Gate produces a high when both of the inputs are high. So look at the Nandi Gate. It produces a high when both of the inputs are high. So which means here we are going to look for where there is B and where there is C, and we consider those as Nandi gates. So looking at my board there, we are looking at B and C now to produce a Q. And we've been told that when in the Nandi gate, when both of the inputs are high, it will give you a high. So we can compare B and C. There is 1, and there is 1, which means at this region, I'm going to get a 1. Then where else at the bottom there is both of the inputs are 1 for B and C. It simply means there I'm going to have a 1. So the rest, they are different on B and C, which means the rest are going to be zeros. It only gives you a high when both of the inputs are high. So if you sort out this mess now, that's when you can get X. So if we see from our diagram there, where is our X? Our X, we are going to find X when we have P and we have Q, which we've managed to get. Now, these two, P and Q, will go into the OR gate. And according to the properties of the OR gate, we say that it can give you a high as long as there is a high in the input. Where is the OR gate? The OR gate is there. You see, as long as there is 1 in the input, it will give you a 1. But when both of the inputs are zeros, it will give you a 0. Don't worry about this. I'm recording this, And after this, I'll put it on my YouTube channel. If you forget my explanation now, you can go to my YouTube and look at it again, and you will be able to answer the question that I'll give you today in the WhatsApp group for grade 10. I'll put it there. Make sure you do the assignment and let me have it tomorrow, latest 18 hours. Later than that, I'm not going to mark your work. You're going to submit your work. Inbox me in my WhatsApp. I'll print and I'll mark. So the OR gate, it's going to give us a high when there is a high in the input. But if there is no high, there is no one, then it's going to be 0. So that's how we got here. Q and P are the input. Let's find the X. They are going through the OR gate. So we have now Q, we found Q, and we found the P. So those two, they are going through the OR gate. And the principle is that as long as there is a 1 anyway, it will give you the output of 1. Their output of 1. We jump there, there is 1. Where else at the far end? As long as there is a 1 anywhere, it means to give you a 1. If there is no 1, then you just put the zeros. And this is the correct truth table for the problem that we have been given. So I'll be sending the PowerPoint I'm showing you. I'll put it in the WhatsApp group. At the bottom of that PowerPoint presentation, there is a question that you are going to sweat to understand. You will need to sweat to make sure that you've answered that problem correctly. So there are 3 inputs there. The first thing you're going to do is to draw the truth table. After drawing the truth table using 2 to the power n, I can see, I know you've got 3 inputs. So just to help you, I think there you're going to put a symbol to find the input for this one. Don't know what you can put there, maybe D, it's up to you. I don't know what you're going to put here, maybe K. Then these 2 inputs are going to be, the output for these 2 are going to be the input for that. Then there as well, the OR gate and the C will be going into the Nanji Gate. So there you're going to have a value, you're going to find out where this and this, they are going to be calculated. So this is a serious issue that I'm giving you. And if you get this thing right, it simply means you will never fail any of the questions on the logic gates. And I hope we are going to review it after you have submitted all your assignments. All right. Any question? Any questions? We've understood? Okay, it's not a big issue. Yes, Costa.
Do we write it in the back of the book or the front?
It's better you put it in the book, because these notes, I want them in the book. From there, even the example, you put it there. Then you answer in your book. Then you get your camera, capture, and WhatsApp me the result for the work I've given you. Does that answer your question, Costa?
So I guess in the back or the front, sir?
Where we ended, continue from where we ended. In your books, continue from there, put these notes in your book, then answer them in your book, then your answers, just capture the answers and send them to my WhatsApp. Please make sure that you put your name there. Or when you WhatsApp me, just say that I'm Costa. You are so many, and most of you have not been putting names like the grade 12. I have a problem with them. So make sure when you WhatsApp me, you also include your name. Message in the message, you just say, this is Costa, this is my work. I'll be able to know that the result for this one is for Costa. Anyone else? All right, too much of talking. Now, how have you been out there? It was a long time. How have you been, Chipo? So at least here, I'm able to see Lumono is there, Juana is there, Tierra, Shama, you are there, Pasco is there, Namalea, that's good. Kalumbo is there, Nyambe, you are there, Caleb, Namalea, you are there, Mapalo. Okay, good to see that a number of you turned up, and this is a very important topic. And if you have no questions, I'll be closing the meeting, and in 5 minutes, your video will be on YouTube. You just set Matthew's Warrior, and when you set Matthew's Warrior, you'll be able to see today's video out to this G10 Logic Gates. And I'll put what I'm supposed to put in the WhatsApp group. Yes, Costa, you have another question?
Yes, I just wanted to say, even when you'd see, it would take longer for you to find it if you're not subscribed to your channel, huh? With the notifications.
Did you subscribe?
Yes.
If you really subscribe, you will receive a notification as soon as I just upload the video.
Receiving all your notifications.
What did you say?
I've been receiving all the videos you've done.
That's very good, but you've not been commenting. I would know that you are watching if you comment.
I don't think you can comment on your videos. Let me double check.
All right. Thank you very much for following up. The Turkish girl, how are you?
Lumba.
Are you okay?
Yeah, I know. Lumba. Lumba.
Lumba, are you okay? She's left the camera there and she has disappeared. Mudenda, how are you? All right, bye for now. And you will receive your work very soon in about 10-15 minutes. See you next time.
See you next time.
Thank you.
Peace out.